I would like to welcome the next speaker. His name is Jaime Orellana. He is a biological engineer. He studied in Germany, in Kiel, at the university. He made his PhD in 2006, and now he's working for Sander Apparatebau, which is known to produce aquaristic equipment as ozone machines. And he will talk about foam fractionation and ozone. Please.
Thank you, Mr. Chairman. You forgot to say that I am the last one.
Yes, yeah.
So it's, thank you very much. Hello, everybody. Buenas tardes, señoras y señores. I would like to thank, first of all, the EUAC meeting for accepting my paper and for allowing me to talk to you today. And I will also thank the organization committee and especially the people from Valencia. You know that life is very simple, or let's say can be simple. So if we had a chance to make an aquarium like that, maybe none of you and myself, we had a good job. But you know better than I am that this is not the situation. So let's go back to reality. And if this is an aquarium and we are recycling the water, it goes one spot of the aquarium out and then back again. It looks very simple, but let's see, this is a flow-through system, so there is no life support system at all, so you just exchange it 100% of the water per hour. But as soon as you start to add some kind of filtration, and if you start to close this life support system, the system is beginning to have a high degree of complexity. Some of the things that are working here, we know that they work perfect, and we know exactly what is happening inside there, but some of them are like black boxes, so you know there is an effect, but you don't know what is happening actually inside. And when you closed almost 100% the water cycle, which is very good for maintaining the water quality and the water welfare of the fish, and for example aquarium that are working with marine waters in the middle of nowhere, let's say in the middle of Germany or many kilometers far away from the next seawater coast. We don't have to forget there is also the human component in here. Maybe you know it, that you can have the best technique in the world, but if you have a very bad personnel, that it's not working actually very good. This complexity has four main issues. The first of them is that there is a high investment cost because the filtration technique for, let's say, 100% recycle system is very expensive. You have also, after you do this investment, you have this operational cost, which is energy in most of the time, and those are very high. Then such a system is quite sensitive due to high automatization. So this is also, let's say, a very inconvenient aspect. And last but not least, you have the requirement of qualified personnel, as I said before. And all this effort, all this operating expense, the sum of them makes that you want to have a good water quality in terms of visibility, because good water quality sometimes it not necessarily means a very crystal water, but most of the people in this world have no chance, for example, to have a view like this one, to go to the Maldives or to the Red Sea and to dive to see the fish on site. So what we did is that we take the fish out of their natural environment, we put them in some aquaria, so that the common people, a grandmother or a 5-year-old child, can have very close an impression of what this natural environment looks like. So at the end, this is the main aim of the thing. And so in this case, for me, particles are actually very good ones, otherwise we are not having a life support system, but also very bad for the water quality and for the visitor. And I want to bring to you now many aspects about particles. Some of them are not really applicable for aquarium, more for high production system, for aquaculture system, but anyway, it's quite interesting. You know, particles, they consume oxygen through biological degradation in the tank, and this can drive, when it's really going bad, to anoxic conditions. Particles, degradation of organic substances, you know, increase the concentration of dissolved nutrients, which is called leaching. Particles can stimulate the growth of heterotrophic bacteria in the tank, which are going to be compiled very competitive against autotrophic bacteria in a biofilter, for example. Particles can be also substrate for facultative pathogens. They can clog mechanical and biological filters. They can influence the efficiency of nutrifiers in the biofilter due to a high carbon to nitrogen ratio in the water. And also they can make damage to the fish, lesions in gills, fins, and on the epidermis. If we look now what possibility do I have to remove these particles from the water, then you have one classification of particles, which are suspended solids, solids in the water column, colloidals, and dissolved substances. Dissolved substances, you know, it's nitrogen components or phosphate, things like that. And colloidals are nor suspended solids, neither dissolved substances. The best example for colloidals is, for example, milk or a hand cream, which is it's a chemical mixture, but the substances are not dissolved in the water. And for other people, you have just large solids, settleable solids, which are able to sink in the water column, and non-settleable solids. And then you have the scale of the particle size. And these are some of the filtration systems that you probably know. You have macro and micro screens, sedimentation tanks, settling tubes, sand filters, skimmers, cartridge filters, even membrane filters that are even, it's possible to get the dissolved substances from the water. But as you probably already see, there is no one single unit that can take all this spectrum of particles out of the water. That's impossible. And this is what we call the two-step solid separation. So there is the need of have different separations methods for particles in the water, big ones and small ones. Those who don't know me, I'm a Chilean actually, and I grow out with this picture, which is in 4,200 kilometers of coast in Chile. And I was wondering when I was a boy why the foam on the beach was so dirty. And there was some substrates or some substrates like water, air, and particles that are playing a role. And these particles are most of them organic substances. So what we did in a foam fractionation is that we have the same scenario more or less, but we just put water and air in a countercurrent inside a tank. And we have also the organic substances, so we are like making the same what is happening in the nature, but we are simulating just in a tank made out of plastic. This is an example of what is happening actually when you are seeing that the water is foaming. You have air, you have protein molecules, and you have suspended particles, bacteria, dead cells, whatever. So you have in the phase number one, there is no organization at all in this scenario, but then the protein molecule has an hydrophobic and which don't want to stick to the water, and an hydrophilic end that likes the water. So this one is then arranged to the gas bubble, and then because of the electrostatic charge of the particles, which is natural, then they stick to this protein molecule that is actually acting like a bridge. And for sure the bubble wants to go out, and the only chance to go out in this reaction tower is to go up, and then it's this foam taking place. And here you see in the picture, which is a magnification of just gas bubbles, and you see the dirt attached around the bubble. This is the head of the skimmer, where you can see the foam forming. And so you had this foam head, the foam tube, which is actually the foam formation taking place, and transport. And you have the interface between water and atmosphere. So when the foam is being formed in this interface, it has to go out. So what we did is just to have like a channel. So to save the foam, you have to go here out. And when the foam is going up and up, it's releasing water. So the foam on the top of the foam tube is quite dry. So you don't have any important water loss. And once the foam is on the top of the foam tube, then it goes to the left and to the right around, and then this dirty foam, it's in the foam head, and it's not in contact with the water of your aquarium anymore. This is another picture of a foam head, and there is two systems just to make the foaming process very constantly and to wash out the foam that has been produced. One is the foam tube rinsing, which you can see on the picture on the right, and it's just a system that throws water in the foam tube, and there is a brush that brushes the last 5 centimeters of the foam tube. So when the system is not foaming very good, because there is no actually more organic substances to get out of the water, probably there is it's going to dry the suspended solids on the last 5 centimeters of the foam tube. And when it's foaming again, that it's not good, because the foam it's not going to break out very very properly. So that's this is device for cleaning that part of the foam tube. And the other one is to wash out the foam head, so you can discharge the foam to the normal canalization. Maybe two information. One is that the rinsing of the foam tube is made with water from the reaction tank. So all this water that is cleaning the foam tube on the inside is falling back to the reaction tank without any losses. And the foam tube rinsing from the outside is done with normal tap water, so it goes back to the canalization. This is how the reaction tank or the skimmer has been constructed. You have a pump, an injector, which is a normal venturi, and air sucking. So by combine this, you are taking water out of the bottom of the skimmer. You are adding gas through the injector, and then you have at least in marine water, the ability of getting very, very fine bubbles, let's say between half until 1 millimeter. And that's it. You can use it for fresh water as well anyway, but the amount of air that you have to inject into the system is more or less twice as amount of air that you need for marine water, because in fresh water you have much bigger bubbles. I always tell to the people that a protein skimmer is the ideal reaction tank for the efficient and effective mixing of water and ozone. Why is that? First of all, you have the proper retention time of the water inside the skimmer, which is like between 1 and 2 minutes. The ozone has been injecting into the system through an existing pump, which I showed the slide before. You have a controlled foam formation, you have a controlled foam discharge, and you can control also the amount of ozone that you want to inject into the system. And a very new thing is that talking about the injection of ozone through an existing pump, is that if you take one of our Helgoland, which is 2 meters in diameter and 4.5 meters high, the old version of the Helgoland has 3 injection pumps with a total power consumption of 11.4 kilowatts. And this was due to the high prices in energy, not so good. So my boss, Mr. Sanders, said we have to do something, and then he designed a new injector, which for the same size and for the same amount of air, in this case, you only need one pump that has a consumption of 4.85 kilowatt per hour. So you have an energy save of 57.5%, but almost 60% of energy saving compared to the old version. So this is a very important step for us as a company, but also for all the people that are working with this kind of devices or are planning in the future life support system for aquarium. Because as I said before, one of the important things in all this effort that you have to spend to have a good water quality is the energy that you are putting into the system. So this is very good. And many people during the last days come to me and said, yeah, how can I do it with the ozone and the protein skimmer? Because, you know, ozone is very dangerous, and ozone is dangerous, but it's as much dangerous as oxygen or Coca-Cola. It depends on the concentration. So the dots that you see there, for example, is a fresh seawater sample that hasn't seen ozone in its life, and it's you get readings of redox potential value of between 350 and 400 millivolts. So you may know that ozone is very hard to measure dissolve in the water. So what you're actually measuring is the total residual oxidants in milligrams per liter. So we add ozone to the sample of water, and then we see that, okay, for having a good water quality, but also the welfare, taking care of the welfare of the fish and not having any mortalities and things like that, byproducts, etc., then we are moving in this window only. And this means that your redox potential has a value between 250 and 350 millivolts, and this concentration of total residual oxidants is between 0.03 and 0.05 milligrams per liter. And if you want to do this exercise, which I will say it's very good, you just measure this total residual oxidants in your system with your water, with your life support system, and you can do this curve by yourself. And then you see, okay, maybe in my water in the Red Sea or in the Baltic or in the North Sea, I have a total residual oxidants of 0.05, and that means that I have a redox potential value of 400 volt, and that's good. That's your situation. So this is just an example.
3 minutes, Jaime.
How many minutes?
3.
Oh, okay. So what we don't want to do is to go into this upper red window, which you are almost sterilizing the water, but if you are sterilizing the water, you are also sterilizing the fish, and at the end it's nothing, nor fish, nothing, okay? So we don't want to go into that high amount of ozone into the water. The advantages of the use of ozone is it has a very high oxidative capacity. It doesn't it doesn't go into the organic salt content of your water, so it's not going to act with any parameters about the salt content of your water. So that's not going to be changed. It's not a pollutant. It has no color. It has also no odor, and so there is no harmful influence for the animals in the system, and also no residual effects, as you may probably have seen, for example, if you are putting chlorine into the water. And by adding ozone, you have zum Beispiel the possibility to oxidize some nitrate. If you have a nitrate peak, then you have this camel oxygen demand, which is all the substances that are very hard to be degraded. So what ozone does is that they chew before, and so the chemical oxygen demand is now turning into a biological oxygen demand, which is very good, for example, for substances that can be take out of the water in the biofilter, for instance. Ozone acts on the double bonds carbon-carbon, for example, in a bacteria membrane, so you can kill also bacteria, viruses, and fungi. You can oxidize yellow substances like humic acid or geosmin. By using ozone, I have seen that you can also build some large particle aggregates, so there is a chance after that for other mechanical filtration, for example, to take out these large particles, and it enhances the foam stability. And I have 3 slides. This is the bacteria load in a system, and you can see the high concentration of bacteria in the foam and a very low concentration of bacteria in the inlet, in the outlet. So there is an amount of bacteria that's being harvesting of the system continuously, and these 8 samples are like pictures, but you have to take into consideration that this system is working 24 hours a day. This is particle size distribution in the tank where we collect the foam with ozone and without ozone, and you can see that by using ozone you are having this situation that you have particle aggregates, so you have the chance to take out of the water larger particles. And talking about this fine solid removal, this is a very old story and a very old aquarium, but it's a very good story. This is this pole aquarium in Berlin, in the SAS Radisson, and they fill it with water, and the water has that color. And they said, oh, this is dust from the construction, so discharge the water and fill it again. They fill it again, it was the same color. And then they had this idea, okay, maybe we have to turn on the life support system. And after a few weeks, this is the same picture, and then you have the clarity of the water, okay? So this is just like an impact. And yeah, that's all I have to say. Thank you very much for your attention.
There is time for, let's say, one short question.
I can see.
I can see anybody. Okay, thank you very much.
Yeah, thank you.
Jaime.